Yeah, so good evening, everyone. Okay, so I see that nobody has joined yet. Okay, so I'll wait for a couple of minutes. If not, I will start the classes today. Okay, okay, let's wait for 1 or 2 minutes. Okay, so let's start for today's classes. Okay, so in today's classes, we will be solving 4 to 5 questions related to your electrostatics or electrodynamics. Okay, which you have already seen most of them. Okay, so but before that, let me just give you a certain few formulas. Okay, just a revision for you. Okay, you have already seen this for a long time. I mean, many in every even from your bachelor's, you must have done this Gauss laws and so on. So for these classes, I will just write few of the formulas that you will be needing, okay, to solve a certain specific problems. Okay, so if you talk the first very important um, formula or laws is Coulomb's law. Okay, so Coulomb's law says that the force between two charges is given by 1 by 4 pi epsilon naught two charges divided by r squared r cap. So this is how the Coulomb's law says that the force between two charges, okay, is proportional to the product of the charges and inversely proportional to the square and the between to the square of the distance between them. Okay, so that means the higher the distance, the lower will be the force. Okay, the shorter the distance, the higher will be the force. Okay, so that is one thing. Second thing is your electric field. Okay, so electric field is in fact given by E, which is a function of, let's say, distance r is 1 by 4 pi epsilon naught. I will go from 1 to n qi by ri square ri cap. Or in other words, I can also represent this one as force per unit discharge. Okay, so this is how the electric field. So if you want to convert this one into a continuous charge distribution, for continuous charge distribution, for continuous charge distribution, what happens is that you can write E is equal to 1 by 4 pi epsilon naught. Instead of the summation, you can write integration, and instead of Q, you can write dq divided by r square into r cap. Right, so this dq is in fact what, for let's say for line charge, for a line, uh, dq is in fact equal to lambda, which is a function of r prime dr prime. Okay, so if I want to write this for a continuous charge distribution, electric field is 1 by 4 pi epsilon naught g is equal to lambda dr prime divided by r square r cap. Okay, so you just need to replace the value of the charge dq by your term lambda dr, lambda r dr. Okay, so similarly for surface charge, what happens, E is equal to 1 by 4 pi epsilon naught, and instead of lambda dr, you have the surface charge density lambda of r prime r so sorry uh, lambda of r prime d a prime divided by r square to r cap. Okay, so you have to replace by surface charge density, and for a line you have to replace by the charge per unit length. This lambda is defined as a charge per unit length, and a sigma is a charge per unit area, or we also call as the surface charge density. Now if you talk for a volume, your electric field will be E is equal to 1 by 4 pi epsilon naught lambda r prime divided by r square d tau prime. Okay, so here lambda will not lambda, it will be rho, which is the volume charge density, that is the charge per unit volume. Okay, so if you integrate, you will get the total charge, and once you get the total charge, you can get q by r square, will give you what is known as the electric field. Okay, so another important formulas that you will be encounter is Gauss law. Okay, what does Gauss law says? Gauss law says that close integration of E dot dA, which is equal to q and close by epsilon naught. Okay, so what does it mean? It means that flux through any closed surface. Why I'm saying a closed surface? Because this is a closed integration of E dot dA. Closed integration is a measure of charge, okay, which is q by epsilon naught. Okay, so this is one of the famous law, which is a Gauss law, which says that okay, whenever the amount of flux passing to a closed Natta surface is actually equal to the charge enclosed inside it. Okay, so we will see how do we need these questions to solve Natta problems. And this is integration form. If you want to write it in the form of differential form, then what happens? You can convert E dot dA, you can convert to sorry. So E dot dA you can convert to so E dot dA you can convert to del dot E equal to rho divided by epsilon naught. Okay, so how do we get this rho by epsilon? Cancel this one. Del dot E is equal to rho dot epsilon naught. We can get it by converting close integration of E dot dA is actually equal to volume integral of del dot E dV. Okay, and how does this q and close? Q and close is actually equal to rho dV. That means charge per unit volume into the dV integration, you will get q and close, the total charge. Okay, so if you substitute back in this equation 1, you will get del dot E is equal to rho by epsilon. This is what we call as a differential form. Okay, differential form, not integration form, differential form. Okay, that is one thing. Next, that is the Gauss law. How do you find the electric field? So from here you can also calculate that what is the electric field. Okay, the electric field strength. Now other than that, you also have potential. Okay, potential. So potential is actually given by, is related to electric field. E is equal to minus of del V, that is the gradient of your potential, and V is given by, from a point charge, V is given by 1 by 4 pi epsilon naught q by r. Okay, and since del dot E is equal to rho dot by epsilon naught that we have just obtained from Gauss law, and E is equal to minus of del V, then you can replace, suppose this is 1, suppose this is 2, put 2 in 1, what do we get? Del dot E will get del dot of minus of del V equal to rho divided by epsilon naught, which is equal to del square V is equal to minus of rho divided by epsilon naught. This is what? This is your Poisson's equation. Okay, and if rho equal to 0, then your del square V equal to 0, this gives you what is known as Laplace equation. Okay, so from here you see that we have talked about the Gauss law, how do you calculate electric field, and how does the electric field is related to the potential also enthalpy. So we will solve first the first problems. Let me just check the first problems. Yeah, so we will first solve the first problems, which says that one, which says the first problems from your assignment. Okay, this is the week 6, so assignment number, question number 1. So okay, let me remind also that whatever as far as this topics is concerned, you can follow the electrodynamics by Griffiths. Okay, you can follow that book. That book contains almost all of the information that are required. Okay, so the question number 1 from your assignment says that the charge density, the charge, CHAR, the charge density of an infinite long dielectric cylinder of radius a varies as rho equal to k of r. That means the charge density is given to you here. Okay, radius is also given to you, charge density is given to you here, where k is a constant, okay, and r is the distance measured from the axis of the cylinder. Okay, what is the question? First one is find the magnitude of the electric field. Find the magnitude of the electric field, let's say E, at the surface. Okay, so if you look at it, okay, how do you visualize it? So there is a cylinder. Okay, so there is a cylinder. Okay, so this is a cylinder, let's say. So sorry, this is a cylinder. So what happens is that there is also at the axis of the cylinder, okay, the radius of this is a, and given that rho is equal to k of r, that means the charge density varies as kr. That means it scales linearly with the radius. Now we have to find out what is the electric field at the surface. So what is the electric field at the surface? That means, let's say, suppose if this is the surface, okay, what is the electric field at the surface or at a radius a? In other form, that means it also asks the question, what is the electric field at a distance a from the axis of the cylinder or on the surface of the cylinder? Okay, so if you want to find out the electric field, like I have just told you, use this formula, E dot dA is equal to Q enclosed by epsilon naught. Okay, so first we need to find out. So if you use this formula, let me name this as equation 1. Okay, so Q enclosed is what? Q enclosed is equal to, you can write rho into dV, that is the total charge. So Q enclosed is the total charge. You can express this in terms of rho as well as dV. Okay, so what is rho? Rho is also given to you to be something like K R prime, isn't it? K of R prime, and this is dV. So if you look back, this is a spherical, this you can replace, not spherical, you can replace this coordinates in terms of cylindrical coordinates, and which is equal to what? 0 to L, this is the length of the cylinder, 0 to 2 pi, this in terms of their angle, and 0 to R, which is the distance. right? So this is you convert this you convert dv in terms of your cylindrical polar coordinates. That means you can replace k r prime dr prime r prime d phi and dz. Okay, I hope you know that this conversion from dv in terms of your cylindrical polar coordinates. Okay, so that means what happens, phi will be equal to 2 pi. If you integrate d phi, you will get 2 pi. Then if you integrate dz, you will get 0 to L. Okay, simply L. And that means the remaining integration, you have 0 to R, k r prime dr prime. Okay, now what happens is that you perform the integration, you will get 2 pi, k you can take it out, so you get k L, and finally your integration from 0 to R of r prime square, you get r prime cubed divided by 3, integration from 0 to R. So that means the total integration 2 pi L k r cubed by 3. Okay, so this is the total charge enclosed. Okay, so now if you look at the equation, what do we need? We need total charge enclosed, we know. Epsilon naught, we know this is a constant. Now we have to solve E dot dA. Okay, so what is E dot dA here? So close integration of E dot dA, so which is a function what? E. And what is the integration of dA? Is the total area of your cylinder, which is equal to simply 2 pi r into L. Okay, either you can perform the integration of dA, or if you know the area of the cylinder, you know this is a radius and this is a distance r, this is a distance r, and I mean the length of the cylinder is L, which is equal to Q enclosed by epsilon naught. Now what happens, you can write 2 into Q enclosed, you can get it from equation, let's say I will name this as equation 2. Okay, so you can use from equation 2, Q enclosed is what? 2 pi L k r cubed by 3, and then 2 pi r L also you can take it out, 2 pi r L into epsilon naught. So that means you get the integration E is equal to simply k r square by 3 epsilon naught. Okay, so this is the electric field at the distance r. Okay, this is the electric field at the distance r, you know. Now if somebody said what is the electric field at on the surface, then what you need to put r equal to A. On the surface you have r equal to A, therefore electric field is simply k A square by 3 epsilon naught. Okay, so if the question is asked what is the electric field at the center, I mean not at the center, at the on the surface of the cylinder, you have to make sure that you are calculating the electric field on the surface at a radius r equal to A. Okay, so the electric field on the surface of the cylinder is given by this problem. Okay, so now, so this is the first problem. Okay, this is the first problem, how to calculate the electric field, on the surface of a cylinder. So what do we do here? We use the Gauss law, simple Gauss law. Okay, you use the Gauss law, E dot dA is equal to Q enclosed. And how do you define Q enclosed? You know the charge density rho is given to be in the form of K of R1, then you just integrate and then put it back in the equation. So it's as simple as straightforward. Use the Gauss law equation and calculate whatever the terms remaining for you. Okay, now we will go to the second questions. Question number 2. What is the question number 2 says? Question number 2 says that two charges, each of plus Q, are placed on the y-axis, at y equal to plus minus of A. Okay, the potential at any point. Okay, so I will rather say at what value of x the potential is half the origin. Okay, so this is I mean, if you look carefully at the questions, it says that two charges each of plus Q are placed on the y-axis at y equal to plus minus of A. That means you have two charges on the y-axis, And what you need to find out is that you need to find out what is the potential at the point x such that the potential is half the origin. So let me draw. What does it mean? Suppose you have this as a y-axis, okay, and suppose you have this as x-axis. Okay, so let me do this as x-axis and this is y-axis. And according to questions that you have plus q charge here and plus q charge here. Okay, that means at a distance of this region is a distance of a and this region also is a distance of a. That is what is given in the question. Two charges on the y-axis, okay, at the distance of a. Now you have to find out the potential. Let's say at the potential at the point P, okay, which is a distance of x, such that the potential at the point P is half the potential at the origin. Okay, that means what happens is that we have to find out due to these two charges, what is the potential at the point P and what is the potential at the point at the origin, such that the potential at the point P it should be half the potential at the origin. Okay, that is what is the question. So if I want to extend the distance here, what is unit? This is equal to simply a square plus of x square using Pythagoras theorem, because this is x and this is a, so you'll get x square plus of a square. This is Pythagoras theorem. Similarly here also, this is root over of a square plus of x square. Why do I need this one? It's because you have to calculate the potential. So potential is given by, you remember, potential at any distance of r is equal to 1 by 4 pi epsilon naught q divided by the distance, right? Q divided by the distance. But now there are two charges, so it will sum up. Okay, so what is the total potential? The total potential at the point P is equal to Q divided by 4 pi epsilon. Let's say my distance r1 plus Q divided by 4 pi epsilon naught r2. Okay, r1 and r2, that means let's say r1 is equal to r2 is equal to root over of a square plus of x square. Because if you look at it, plus q and on the positive side and the negative side also, they are the same distance of root over of a square plus x square to the point P. Okay, to the point P here, to the point P. Okay, so now if I want to write it out, it will be simply q, and you substitute r1 and r2 simply a square plus x square. You will have q divided by 2 pi epsilon naught root over of x square plus a square. So this is your potential at the point P, okay, which is at the distance x from the origin according to these questions. Now what is the potential at the origin? What is the potential at the origin? What is the potential at the origin? That means at the origin, what does it mean? It means that you are talking about this point here at the origin. So the origin means is clear that your x equal to 0, right? So your x equal, but your y is equal to a. This is at the origin. Because your charge is at the distance a, so you are going to find out what is the potential at the origin where x is equal to 0. Therefore, your potential is equal to q divided by 2 pi epsilon naught. Instead of x square plus of a square, you will simply get a square, which is equal to q divided by 2 pi epsilon naught a. So now you know the potential at the distance of at a point P, right? At a point P, or I can write here Vp, that will be better. What is the potential at the point P, and you also know what is the potential at the origin. Now what happens? You need to find out to find v of x equal to half v of 0. That means you have to find out at what position of x is the potential half at the origin. Okay, that is what is the question. What is the position? That means you have to find out what is the value of x, this x, such that the potential is half the potential at origin. So that means v of x is equal to half v of naught, which is equal to v of x, you know, you can take it from here. V of x is equal to simply q divided by 2 pi epsilon naught root over of a square plus of x square equal to half. You know, also know v of 0 from here. This is the origin, will be simply q divided by 2 pi epsilon naught of a. Okay, now you can cancel q and q on the left hand side and the right hand side 2 also you can cancel, pi epsilon also you can cancel. So the only remaining term is 1 divided by root over of a square plus of x square equal to 1 divided by 2a. This is the remaining term. Okay, then after that what you can do is that you can write a square plus of x square is equal to 2a. Okay, and what then you can square both sides. You can write x square plus of a square equal to 4a square, and finally you can write x square is equal to 3a square, and x is equal to plus minus root 3 of a. So this is the distance in which your potential is equal to half the potential at the origin. Okay, so that is what you need. Now I think I have not given you certain. Yeah, I think I have given you. Yeah, so yeah, from here let me also just add a little. Okay, let me also add a little here, that your formula, how do you calculate the potential? Okay, so okay, let me just add it here at the back, that will be better. Yeah, so in this case we have used the formula, what v is equal to 1 by 4 pi epsilon naught q divided by r. Simply this is the potential due to a point charge. Okay, so that means what is the potential? The potential v at a distance r, from a single point charge q is defined as the work done to bring a unit positive charge from infinity to that point. Okay, that is why you are giving v of r is equal to 1 by 4 pi epsilon naught q by r. Okay, so that means what is the potential? Let's say you have a point charge plus q, okay, which is at the distance r. Okay, so let's ideally what does it mean? It means, so suppose you have a point charge plus q, and suppose this is the point p that which is at the distance of r, and what is the potential at the point p from this charge plus q? So it is defined as the amount of work done in bringing a unit positive charge, let's say plus q, from infinity to this point. Okay, so how much work you require to bring this charge plus q to the point p, that is in fact what is the potential. Okay, so the potential is in fact what? 1 by 4 pi epsilon naught, simply q, that is due to the point charge plus q, and what is the distance r? That is the distance of r is to the position where you want to find the potential from the point charge plus q. Okay, so if you have, let's say there are many charges, this is called as the superposition principle. Okay, if there are many charges, then what is the potential will be equal to v1 plus v2 plus v3 plus and so on. That means ideally you have q1 here, q2 here, q3 here, and you want to find out what is the potential at a point p. Suppose this is given by r1, this is given by r2, this is given by r3. Then what happens? You will get something like, I will go from 1 to, let's say, to point n, not point n, to n number of charges. We can just 4 pi epsilon naught of r I. Okay, so in the second problem which I have just solved to you, this problem 1 by 4 pi epsilon naught q by r is in fact the same thing which I have shown you. What is the potential due to a point charge, which is equal to 1 by 4 pi epsilon naught simply q by r. Okay, now there is another problems. Okay, so yeah, so if I want to solve, I can solve now the third problems. Okay, these are pretty straight forward problems. Okay, which is also available in many books. Okay, so the third problem is slightly different, but more or less it follows the same formulas. Okay, so the question is says a point charge, a point charge q is placed at the center, okay, at the center of a thick spherical shell of inner and outer radii r1 and r2. Okay, remember this, respectively respectively uh, calculate the electric displacement the electric displacement vector, the electric field E, and polarization P. Okay, for region 1, for region R, less than the radius R1, 2 is R greater than R1 but less than R2, and third is R greater than R2. Okay, so what does this question means? Okay, let me just draw it so that you can understand. So in this, what happens that you have a spherical shell. Okay, you have a spherical shell, and this one is in fact radius r1, okay, and this one is r2, okay, and this region is given by the permittivity epsilon. Okay, so there are two regions. First of all, you have to find out what is the electric displacement, you have to find what is the electric field, and you have to find the polarization. Okay, so there are three regions that you have to find out. One, r less than r1, that means this region, let's say I'm naming this as region 1, okay, and region 2, let me name this as region 2, in which r is greater than the inner radius r1 but less than the radius r2. Okay, that means this region 2 here, and then this is the region 2. Let me just name it here, let me just name it as a region 2. Okay, let me name this as region 1 and region 3. Region 3 means r is greater than the r2, that means it is out of the spherical shell. R1 means less than the inner radius, R2 means in between radius, inner radius and the outer radius, and the third region means outside of the outer radius. Okay, so if you look the Maxwell's equation, or I will not go to Maxwell's equation at the moment, you just go this simply E dot dA equal to rho divided by of epsilon. Okay, this is in vacuum. Now this is in vacuum, where epsilon is the permittivity in vacuum, right? And this is we obtain from Gauss law. Now, but if it is not a vacuum, then what happens? You can write the same equation as d dot dA equal to q free. Okay, where d is in fact what? D is equal to epsilon of the electric field. Okay, so d dot dA is actually q charge. Now what happens? That means how do we do this? It's the same thing. So since it is a sphere, or it is a spherical shell, then you have d into area is simply 4 pi r square is equal to something like q, and the electric displacement is equal to q divided by 4 pi r square. That means the electric displacement vector d, which is equal to q which is equal to charge, okay, which d dot d is equal to free charge, q free. That means d into 4 pi r square is equal to simply q, and d is equal to q divided by 4 pi and the r square. So this is the same for all the regions. For all the regions I can write, for all the regions d is equal to q divided by 4 pi r square. Okay, that means for all the regions your electric displacement vector is the same. Okay, that means it depends upon your r square, but it changes when you have to calculate the electric field. So this is where it becomes important now. Okay, this is where it's important. So you have to calculate electric field and polarizability. Okay, electric field and polarizability. Because why? What happens is that if you go back at the question, what happens, it says that a point charge plus q is placed at the center of a thick spherical shell of inner and outer radius r. So I forgot to place, there is a point charge plus q here. So you have to find out what is the electric displacement, what is the electric field due to a point charge, and what is the polarizability. Okay, so the electric displacement vector, as we have seen, is remain the same, which is given by q divided by 4 pi r square. That means it depends on your r square term. But when you talk about the electric field, now the relation between d, the displacement vector, electric field, and p r, d is equal to epsilon of E, right, where epsilon is in fact epsilon naught E plus P. Okay, so here P is the polarizability. Okay, that means epsilon E is in fact equal to epsilon E plus the polarization P. Okay, so so now what happens is that we can find, let's say, region 1. In the region 1, what happens? R is less than R1. Here what happens in this region? Permittivity is simply epsilon 1. It is simply vacuum. This is in region when R is less than 1. That means what happens? Your electric field, you know, from Gauss law again, from Gauss law you get q by 4 pi epsilon naught of r square. Okay, this is one. Or you can also write simply E is equal to d by epsilon naught. Okay, in vacuum this equation valid, E is equal to or d is equal to epsilon naught of E in vacuum. Okay, so that means you know the value of d from this equation, q divided by 4 pi r square. So that means E is equal to which is equal to q divided by 4 pi r square into 1 divided by epsilon. So you get electric field is equal to 1 divided by 4 pi epsilon r square. Okay, so that is how you can easily calculate. Knowing the electric displacement vector, you can easily calculate the electric field in vacuum. Okay, now again in region 1, we are talking about the region 1 now. Okay, you know the electric displacement vector, which is equal to q divided by 4 pi r square, and now the electric field, you know, q divided by 4 pi epsilon r square. And what happens now? Polarizability is equal to what? If you look at this equation, is d minus of epsilon E. So d minus epsilon of E. So what is d? D, you know, q divided by 4 pi r square minus epsilon. Electric field also you can take it from here, q divided by 4 pi epsilon naught r square. So now what happens? Epsilon will get cancelled. This term will get cancelled with this term. You will get 0. Okay, that means in region 1, polarizability equal to 0. Now let's move to region 2. What is the region 2? R is greater than R1 but less than R2. Okay, displacement vector is the same, q divided by 4 pi r square into r cap. Let's see if you want to write the direction also. Now electric field is equal to what? D by epsilon. Remember that it's not epsilon naught anymore because the permittivity is different now. In the region 1, in the region 1 you have epsilon naught, but here in the region 2 you have epsilon, not epsilon, because it is not a vacuum anymore. Okay, It is a thick spherical shell of inner and outer radius R1 and R2, and also with permittivity. I forgot to mention with permittivity also alpha. So in this region 2, now there is a permittivity alpha, not sorry, not alpha, epsilon, not alpha, epsilon. Okay. In the region 1, you have a vacuum permittivity, but in the region 2, you have what? You have a permittivity given by alpha, not alpha, epsilon. Sorry. So now instead of vacuum, in vacuum you have E is equal to D by epsilon, right? In a non-vacuum, what happened? D is equal to E is equal to D divided by epsilon. Okay, so what we'll do again, Q divided by 4 pi r square is the electric displacement vector, and epsilon you can get it here. You can get simply Q divided by 4 pi epsilon of r square. Okay, so that is electric field. The electric field, you know. Now polarizability, again the same thing, which is equal to D minus of epsilon of E. Okay, so D is, you got it, which is equal to Q divided by 4 pi r square minus epsilon naught, and electric field is a Q divided by 4 pi epsilon of r square. That's it. This is r cap. This is also direction of r cap. Now remember that in the previous case, in the region 1, here is also epsilon naught. In the bottom you have epsilon naught. So that means epsilon gets cancelled. But here it is not so, because it's not the same permittivity. So that is why you cannot cancel. So you will get what? You will get simply Q, you can take common 4 pi r square. You will get what? 1 minus of epsilon naught divided by epsilon of r cap, which is equal to simply Q epsilon minus of epsilon naught 4 pi r square epsilon of r cap. You see, now the polarization is not 0 anymore. It's in fact some positive value. Okay, now this is the region 2. Okay, now if we go to region 3, what happens to region 3? In the region 3, again r is greater than r2. That means it's outside. So outside you can consider it as a vacuum again. Okay, if you consider as a vacuum, you know, D is the same thing, Q by 4 pi r square into r cap. Okay, then what else? You have electric field, which is equal to D by epsilon naught, which is equal to what? Q divided by 4 pi epsilon naught of r square into r cap. Okay, and finally what? And finally, polarizability is equal to D minus of epsilon naught of E. This is the formula. So D, you know, Q by 4 pi r square minus epsilon naught. Electric field, in way you know, you can write Q divided by 4 pi epsilon naught of r square r cap. This is also r cap. Epsilon will get cancelled. This is equal to 0. Okay, so if you look at it, okay, your polarizability is non-zero only in region 2, otherwise it is 0. So if I just summarize, what happens if I just summarize? Therefore, for r less than r1, that is inside, what happens? You have D is equal to Q by 4 pi r square. If you want to write the direction r cap, then electric field is equal to what? Q by 4 pi epsilon r square, whereas polarizability equal to 0. Now in region, this is in region 1. In region 2, what happens? R is greater than r1 but less than r2. Okay, so what happens there? The displacement vector remains the same, Q divided by 4 pi r square and to r cap. Electric field also remain the same, which is equal to Q divided by 4 pi, not epsilon naught anymore, it will be simply epsilon r square, because the permittivity is different in region 2. Now polarizability, because of that you also have polarizability, which is equal to Q divided by 4 pi epsilon r square epsilon minus of epsilon naught, let's say r cap. Okay, finally you talk about the region, you talk about the region 3, in which r is greater than r2. Okay, r is greater than r2, then you have D is equal to Q by 4 pi r square r cap, and electric field equal to Q divided by 4 pi epsilon naught r square, and the polarizability equal to 0. So for okay for I think I saw someone just join. So let me just recap of what we do in this class. Okay, so in this class we have solved three questions. Okay, three questions we have solved, and um, I have solved the three questions of your week six yeah the week six assignments, okay, which is related to your electrostatics or electrodynamics. Okay, so what of the important formulas, let me just remind you. One of the important formula is your Gauss law, which is given E dot dA is equal to Q charge enclosed by epsilon naught. That is the first. Second is your potential, which is given by 1 by 4 pi epsilon naught Q dot by R. Okay, so if I go back to you, okay, whatever I have done, um, let's say for you who just joined, okay, let me just repeat it because I think it will importance. Okay, so if you look at the question number one, okay, for who just joined, okay, what happens is that for question number one is given that the charge density of an infinitely long dielectric cylinder of radius a varies as kr, okay, where k is a constant and r is the distance measured from the axis of the cylinder. Find the magnitude of the E at the surface, that means of the electric field. So if the question is asked finds the electric field, then what you need to do is that you can use the famous Gauss law. Okay, E dot dA is equal to Q enclosed by epsilon naught. Okay, so Q enclosed is in fact rho dV, that is the total integration, and rho is already given to you. You can just do the integration and substitute back in equation 1. And E dot dA also, you know, dA is the area of the cylinder, which is equal to 2 pi r square L. And on the surface, what you need to do, you can put back R is equal to A. I mean, you can put that R is equal to A, you will get the electric field. So in the first question of your assignment, we use the Gauss law. Okay, simple, the Gauss law. Next, in the question number 2 is given that two charges as plus q and minus q are placed at y equal to plus minus of a, and at what value of x the potential is half at the origin. This is also pretty straightforward. You just need the potential. V is equal to 1 by 4 pi epsilon q divided by r, but since there are two charges, you place the summation. Okay, 1 by r1, 1 by r2, and then you calculate what is the potential at the point x. Then and then you also calculate what is the potential at the origin, and finally to find v of x is equal to half of v of 0, you will get what is the value of x. So the first question we use the Gauss law. Okay, I can provide you the notes whichever I have written, you can follow it up. But in the first question, just remember that we have used the Gauss law, and the second equation we have used a simple equation, I mean the potential due to a point charge, which is equal to 1 by 4 pi epsilon naught q by r. Okay, and the third questions is also the same thing. And the third question also is the same thing. It's like a point charge is placed at the center of a thick spherical shell, like this region, thick spherical shell. Okay, and this spherical shell has in this region R2 or in this regions greater than R1 and less than R2 is given by epsilon permittivity alpha. Okay, and inside it is like in a vacuum, and outside it is also is a vacuum. So what you need to find out, displacement vector, electric field, and polarization. Okay, that is also I have given to you what I have given. Instead of using this is also the Gauss law. Okay, this is also the Gauss law, but in the presence of a medium, not in a vacuum, is d dot dA is equal to q charge. Then it's the same thing. dA is for a spherical shell is given by 4 pi r square, and the electric displacement is simply q by 4 pi r square. And similarly, from there you can also calculate what is the electric field, right? D is equal to epsilon of E, right? D is equal to epsilon of E. That means you can calculate what is the electric field and also the polarization. So here is a pretty straightforward formula. Okay, you just need only to use only the Gauss law, and also the potential like the potential due to a point charge. Okay, and everything that you will be able to just write. This is a simple problems. And now that there are three parts in this question number 3, which is says that okay, less than R1 you have a vacuum, greater than R1 and less than R2 you have a permittivity, which is a medium, which is given by permittivity epsilon, and outside of it R greater than R2 is simply a vacuum. Again, it will be the same thing as your region 1. So if I try to if I try to recollect it, what does it mean? It means that a spherical shell is given like this, and this region is given by permittivity alpha, this region is epsilon naught, and outside of the region is also equal to epsilon naught. and this is the region, sorry, this is the region R1, and this is the region R2. Okay, so this is the region 1. R is less than, let's say a distance R is less than R1. This is the region 2, in which it is in the middle between inside and outside, and this is the region 3. Okay, simple. Okay, so what we have used simply a Gauss law again in this equation. Okay, now I have two more problems to solve. Okay, then it will be finished for this class. So let me just solve the last two questions and then we will stop. Okay, so the next problems is slightly different. Okay, the fourth question is slightly different. It says that a charge Q is kept at a distance 2r. Remember, a charge Q is kept at a distance 2r. Remember this terms is a charge Q, and also is kept at a distance 2r from the center of a grounded conducting sphere. Remember, this grounded conducting sphere is very, very important. Okay, it's different than whatever you have seen, but it is a grounded conducting sphere. It's given to you a grounded conducting sphere of radius r. Okay, of radius r. Now find the magnitude of image charge. Okay, this is also very important. Find the magnitude of the image charge. Then at what distance it is located relative to the center of the sphere. Okay, this is the inter questions. Okay, I just repeat, and draw a neat diagram. That's the next question, is draw a neat diagram. Okay, and showing the position of the image charge. I will not write the whole question. Draw the neat diagram showing the position of image charge and original charge, and what is the force between them. Also, what is the force between them. Okay, it's slightly long, but I'll show you. So before we go to this problem, let me just quickly tell you a little about, to solve this problem, to solve this type of problem like a conducting plane, you use this concept, method of image charges. Okay, to solve this problem, okay, I will explain it again, but to solve this problem you use this concept of method of images. It is available in the Griffiths book. Okay, look there, like Introduction to Electrodynamics by Griffiths. It explains very well how do you get this. This idea is because suppose there is a charge Q, that's it, at distance d above an infinite grounded conducting plane. In the questions, okay, in the main question is given conducting sphere. Here is given as a conducting plane. I just give you an idea. So that means suppose you have a plus charge plus Q here at a distance d from the plane. Suppose this is the plane. So this potential is equal to 0 and 7. So the question is that suppose there is a charge Q held at a distance d from your plane. That means suppose this is a plane with a potential V equal to 0, and you have a charge plus Q above this. So the question is that what is the potential just above the plane? Okay, so the answer is, so the question is, what is the potential just above the plane? Okay, you can see that, okay, so the potential just above the plane is simply 1 by 4 pi epsilon q by r. Okay, the potential due to a point charge plus q. But in fact, no, it is because a certain negative charge also will be induced near this plane because of the point charge plus q. So it's not simply only the point charge plus q, but also because there will be a certain amount of negative charge induced near the surface, okay, of this plane. That is why you will have simply not the potential due to plus q, but in fact you will also have the potential and the due to the induced charges. So if I have to write the answer, it is not only 1 by 4 pi epsilon naught q by r, right? This is the potential due to a point charge plus q which is given to you. It is not simply this point charge plus q, but it is also a certain amount of negative charge on the nearby surface induced by plus q. Okay, so it's not simply plus charge plus q, but there's also a certain amount of negative charges on the surface. So if you have to find out the potential, you have to find out the potential due to this plus q and also due to the induced charges, on the surface. Okay, so but you don't know how much is the induced charges. That is why this method of images comes. You replace the induced charges by another charge. Okay, so instead of calculating what is the induced charges, instead you calculate what is the induced charges, which is given by, let's say, the negative of your plus q. So that is this method of images. Instead of writing the induced charges, you simply write what is the image charge. So that is what is this question is all. So it's all about. So what does it mean? It means that now if I try to answer your question number 4, if you try to answer the question number 4, it means that there is a conducting plane. Okay, there is this conducting sphere, the conducting sphere, and there is a point charge plus q, which is located at a distance 2r. Okay, which is the distance of 2r. Now the question is, first of all, find the magnitude and sign of the induced charge. You know that if there's a conducting plane, again, as I've just mentioned to you, that it's not simply plus q charge, but it's also the induced charges. So the question here is asking, what is the induced charges and what is the sign of it? Okay, so if I have to write, so such problems is solved using method of images. Okay, so what this images says that this method, the method of images, allows us to replace the induced charges, I can write the induced surface charges. I can write the induced surface charge on this sphere with a single point charge called image charge. You understand? That means suppose if you have a point charge plus q, this point charge plus q, and if you want to calculate what is the induced charges on the surface of the sphere, this is your conducting sphere. conducting sphere. So instead of finding out what is the total induced charge, just simply replace by a charge called the image charge. Okay, such that, okay, by the image charge such that the potential on the spherical surface is 0. Okay, I hope you understand what is the image charge. So image charge is in fact what is a method in which you can replace the induced charges, let's say due to a point charge, by a simply negative charge, okay, by another charge, such that, okay, the potential on the conducting plane or conducting sphere is equal to 0. Okay, so that means now I have given you this diagram. That means you have a point charge plus q which is located at a distance of 2r. So the first question, the first one, it asks, okay, what is the magnitude and sign of the charge? Okay, so the magnitude and sign of the image charge is in fact given by q prime is equal to minus of r by dq. Okay, so q prime is the image charge. Okay, we replace the induced charges by simply q prime, and q prime is equal to minus of r divided by d into q. R is actually radius and d is distance. And from our problems, what is the distance? From our problem, distance is equal to 2r, right? It's given in the question. So that means you can just replace minus of r by 2r into q, which is equal to simply minus of q by 2. Okay, so the image charge, okay, has a distance or so the image charge, in fact, no, sorry, the image charge is in fact half of q, that is simply q by 2, and what, and it also has a negative sign. So if I want to replace this one, if I want to replace, I can replace it here. Let's say this is my origin and this is my q prime. Okay, instead of representing the induced charges, you can replace simply by q prime, and this q prime is in fact what, minus of q by 2. It is a negative charge, and also the magnitude is half of your plus q charge. Okay, that is the first question. What is the magnitude and the sign? So you already know the sign is negative, and what is the magnitude? The magnitude is half of the original charge, which is q by 2. Okay, now the next question, that is the next question. The next question is, what is the distance from the center? What is the distance mean? What is the distance of the image charge? What is the distance? Let me just write to be clear. What is the distance of the image charge from the center? Okay, so that means what? What does it mean? It means that how much is this distance? Q prime from 0. Okay, what is this distance? The distance is in fact given by what? Let's say b is equal to r square by d. This is the formula, and you know that b is equal to r square by d. You know d is equal to 2r, which is already given into your question. So d is equal to 2r, which is simply equal to r by 2. Okay, so the distance of the image charges from the center is simply r by 2. That means if I want to draw here, this is in fact r by 2. And let's say this is your radius r. Okay, so so this is pretty easy. Okay, you just replace by the induced charges by q prime, which is an image charge. Okay, and the third, if you look at the third questions, okay, if you look at it, okay, let me just go back to your questions. The first in, find the magnitude of the image charge, that we have done, and the sign we have done. At what distance it is located relative to the center of the sphere, that is also we have done, which is the second. The third is, draw a neat diagram showing the position of image and the original charge. So the draw a diagram is simply this one which I have drawn, exactly this one, the third one. Okay, the third question is, this is your question number 3, answer number 3, answer number C. Okay, to draw the neat diagram showing how does the image charge plus q and the original charge are placed. Okay, so if I want to redraw it, the question number 3 is simply this one. Again, it's the same thing. What you have to do, this is your sphere, this is your point charge plus q, this is your origin, this is your distance r, okay, and distance here to here is d, which is equal to 2r, right? And what happens, q prime is located somewhere here, and q prime is equal to what? Is simply minus of q by 2. And what is this distance? Is r by 2. Okay, if okay, the third question is show the neat diagram. So you just need to show this diagram. Okay, it will be enough. Okay, or you can write here maybe conducting plate, okay, which is grounded. Okay, now the fourth question is find the force. Find the force between your q prime and q. Okay, so that is the question. So now q, you know, from the origin is r, is 2r, and this distance is r by 2. So what is the distance between q prime and q? Distance, because you need the distance. This is Coulomb's law. F is equal to 1 by 4 pi epsilon q1 q2 by r square, right? So r square is the distance between the charge q1 and q2. Now also you need to know what is the distance between this q charge plus q here and this q here. So what is the distance here? Distance between q prime and q is what? You know, you can write as to be equal to what? 2r minus of r by 2, right? Because 2r is from the origin and r2 is the origin to q prime. So distance between q prime and q, you can take 2r minus of r by 2. You'll get the distance of, which is equal to 2r minus of r by 2. Okay, so now you know the distance. Simply the force is equal to 1 by 4 pi epsilon naught. So this is q prime, this is equal to q, and the distance is equal to what? 2r minus of r by 2 whole square. Correct? Then what happens? This is in fact equal to 1 divided by 4 pi epsilon naught. Q prime, you know, which is equal to what? Minus of q by 2. So you can replace q prime is minus of q by 2, and this is also equal to q, and 2r minus of r by 2, which is equal to what? 3r by 2 whole square. And what happens? You will get minus of, you just evaluate, minus q square divided by 18 pi epsilon naught of r square. Okay, so this is the force between the point charge plus q and the induced charge or and the image charge q prime. Okay, so that is the end of this questions. Okay, so one more thing, what does this negative sign means? This negative sign means the force is attractive, right? Why? Is because the original charge is q, but what is your image charge? Your image charge is q prime, which is equal to minus of q by 2. So because of this negative sign, so the force between the image charge and the original charge is attractive in nature. Okay, in these questions, the force between the q prime and q is attractive because of the negative sign. Okay, so so these problems, okay, this method is very helpful in such cases where you know, you have to replace the induced charges by a simple by simple and image charges. Okay, so that is the end of these questions. Okay, question number 4. And last questions. Okay, last questions is I think you already know also. It's pretty straightforward. Okay, the third question is write down Maxwell's equation in vacuum and in medium. Okay, write down Maxwell's equation in vacuum and in medium. Okay, this is pretty straightforward questions. Okay, if you have seen that different type of different types of Maxwell's equations. How do we not different types, okay, different how many types of equations are there? You must have seen it. Gauss law is in fact what? del dot E equal to rho dot by epsilon, right? This is the first Maxwell's equation. Second is del dot B equal to 0. This is the second Maxwell's equation, that is the divergence of the field is equal to 0. Third is del cross E is equal to minus of del B divided by del T. This is the Faraday's law. And final is Ampere's law, which is equal to del cross B is equal to mu naught J plus mu naught epsilon naught del E by del T. Okay, so if asked you, okay, there is no name for this. Okay, it's simply that the divergence of magnetic field equal to 0. Okay, if somebody asks you, okay, what are the four Maxwell's equation? These are the four Maxwell's equation. That means these we got from your Gauss law. Okay, I have written this one, del dot E is equal to rho divided by epsilon naught. Del dot B is equal to, this is the divergence of it. And we have not talked about the Faraday's law, but even you must have seen this. Okay, Faraday's law, this is the third Maxwell's equation, and Ampere circuit law, and that is the fourth Maxwell's equation. Okay, so this is J is a current density, E is the electric field, okay, B is the magnetic field, and so on. Okay, now the next there are two parts. Okay, write the Maxwell's equation in vacuum. In vacuum, this is what whatever I have given to you is in vacuum. But what happened in the case of your medium? So in the case of a medium, it's the same thing. It's just like slightly changed here and there. In medium, in a medium, what happens is that the charge density rho is equal to rho bound charge plus rho free charge. Okay, so the first equation, epsilon naught of del dot E equal to rho, so rho B plus rho F, right? This I got it from what? Del dot E equal to rho divided by of epsilon naught, but I replace the rho with simply rho B plus of rho F. So that means rho B is also equal to minus of del dot P polarization plus rho of F. So you will get del dot simply D, sorry, before that I will write del dot epsilon E plus P equal to rho F. How do I get that? We can just substitute rho P and substitute back this equation. So you will get del dot D equal to rho F. So this is also the same formula which I have used when I calculate the displacement vector. If you recollect it, now the del dot D is equal to simply rho F. So now or you can write integration of D dot dA is equal to Q and close, free charge and close. This is the same thing as the Gauss law, but you just instead of just free charge, you also introduce what is the bound charge in the case of a medium. Okay, otherwise it's the same thing. Gauss law remain the same. It's just like a slight modification of your charge. So now if you look at it, then how will be your Maxwell's equation becomes? Maxwell's equation becomes del dot D equal to rho F. This is the Maxwell's equation vacuum. That is the first. This is the same thing as Gauss law, right? Now del dot B remain the same. Okay, del dot B remain the same. Del cross E is equal to minus of del B del T, that is also remaining the same. And finally is del cross H is equal to JF plus del D del T. Okay, this is also the same thing, but you just replace B is equal to mu H. So that means B by mu equal to H. Okay, so if you look back, I have written B is equal to mu naught J plus mu naught epsilon del E del T. So for a medium, what happens then? You carry this mu here. So B by mu will be equal to H, and epsilon del E del T is in fact what? D, which is the displacement vector for you, right? So this is the same thing, except that you just replace your simply epsilon naught, which is the permittivity of a medium, permittivity of vacuum, by introducing epsilon. Okay, and also you have to replace simply a charge by a bound charge plus a free charge. So that means if you do that, if you calculate this one, you will get del dot D is equal to rho F. So del dot D is equal to rho F. This remain the same. Del dot B is remain the same as you have seen, and del cross E also remain the same. This minus del B del T, and del cross S is JF, which is a free current density, plus del T by del T. Okay, so this is the same thing. Okay, so you just need to replace in vacuum and in medium. Okay, but the main equation remain the same. Okay, so this is write the Maxwell's equation in vacuum as well as in medium. Now there is a second question. Yeah, second question. So if I just write this way, D is equal to epsilon of E in this case, and also B is equal to mu H, and yeah, and JF rho F are current, are free current and charge densities. Okay, these equations, you know, are is it's not like I have solved it. Is you have to you know what is a Gauss law, and what is the Ampere's law, what is the Faraday's law. Okay, that's it, and then they combine together to I mean to get a Maxwell's equation. That's it. It's not like I have to solve each of them. No, no. It's like each laws that constitute a Maxwell's that equation law. So if you have to know, if you have to remember, you have to go back to the Griffiths are also there. You have to read what is a Gauss law, what is the Ampere's law, what is the Faraday's law. Okay, and del dot B in a way is a there is no loss for it, so you will see it there also and it's defined in the textbook also, or it's explained in the textbook also. Why? So they will just combine it together to get, yeah, the four Maxwell's equation. But in fact it's related to electric field and magnetic field. At the end it's related to your electric field and magnetic field. Like del dot E is electric field, del dot B is a magnetic field, again the curl of electric field and the curl of your magnetic field. So it's simply the divergence of electric field and magnetic field and the curl of electric field and magnetic field. Okay, so the second question is simply straightforward. Okay, there is a second that is the second part and the third part. Question number B, I will write the same. So for a parallel plate capacitor, okay, which varies as Q is equal to Q naught sine omega t. We have to find out what is the displacement current. You have to find what is the displacement current. Okay, find the displacement current. So displacement current is pretty straightforward. You know that for a parallel plate capacitor, E is equal to sigma by epsilon naught, and that means sigma is equal to Q by A. That is the charge per unit area. So we get Q divided by epsilon naught of A. Now what happens is that flux is given as what? Flux is given as electric field into A, which is equal to simply Q divided by epsilon naught. Okay, so displacement current ID, I will just say, is given as epsilon naught d phi E divided by dt. That is the epsilon into the rate of change of flux with time. So it's easy. Now epsilon naught d phi E, which will simply be d by dt of Q by epsilon naught, right? So epsilon naught and epsilon naught will get cancelled. You will get dq by dt, but Q is given to you as what? D by dt. Q is given to you as Q naught from the questions. From the question is given as Q naught sine omega t. So Q naught sine omega t. So you can just differentiate d by dt of Q naught sine omega t. We get Q naught and then omega cos omega t. So this is your displacement current. It's pretty straightforward. Okay. Now the third part, which is the C, is you have to find out the magnetic field, and electric field is given to you. Electric field is given to you something cos 20 cos omega t minus of kz plus 5 cos omega t plus kz along the x cap direction. So it is given to you, the electric field is given to you, and I have to find the magnetic field. So from the Maxwell's equation, you have what? Del cross E equal to minus of del B del T. Right? You can calculate what is the curl of E, and you can easily calculate what is the magnetic field. So what happens is, since electric field is only along x, why I'm saying along x is because here is given to be along the x cap direction. Correct? It's along the x cap direction, which is along the x axis. Now what happens if you calculate del cross E will be simply I j k del by del x del by del y del by del z. Since there is only x, we can write ex, and this is 0 0. So ideally del cross of E will be what? Simply del Ex divided by del z into j cap direction or the y cap direction, right? So that means del cross of E is in fact is simply del differentiate your Ex with respect to z axis. That means is equal to del by del z, and Ex is what? Ex is already given to you, which is equal to 20 cos omega t minus of kz plus 5 cos of omega t plus of kz. And which direction it will be? Now it will be in the j cap direction or in the y direction, right? So you just differentiate with respect to z. With respect to z is simple. You can get 20, you can write k, because k is coming from this for this differentiation. You get sine omega t minus of kz minus 5 sine, k also will be there, sine omega t plus kz along the j cap direction. Okay, so now you already get del cross of E, which is equal to this term. So now how do you get, how you know that del cross of E is equal to minus of del B by del T, right? So you can easily calculate it, minus, which in fact that del B by del T is equal to 20, this term here, 20 k sine omega t minus of kz, okay, minus 5 k sine omega t plus kz, and this is equal to j cap direction. So how do we get B? You just integrate this. You just need to integrate this. This is pretty straightforward. So what is your value of B? Your value of B is actually integration of this term with respect to dt. Okay, you just need to integrate this term. That means B is equal to, I'll just write the formula, not the formula, the final result, 20 k by omega cos of omega t minus of kz minus of 5 k by omega cos of omega t plus kz j cap direction. Okay, so you can also replace this k by omega simply equal to c. So 20 divided by c cos of omega t minus of kz minus of 5k by omega cos of omega t plus kz j cap direction, because 1 by c is simply k by omega, or omega is simply c k. Okay, so this is the end of your for today's classes, right? For today's classes. So if you look at it, in the first question we solve only Gauss law. In the second question we talk about the potential due to a point charge. Okay, we have to calculate what is the potential. The third questions is again using your electric field and displacement vector, okay, which is again the same thing using the Gauss law. In the fourth problem, there's a slightly difference in which you use the method of images. How do you find the induced charges using the method of images charge? And the fifth questions, this will purely use Maxwell's equation. Okay, how do you solve suppose if electric field is given to you, how do you find magnetic field? So there is a correlation between them, okay, the equation which is given by the Maxwell's equation. And how do you get the Maxwell's equation? The Maxwell's equation you know from your Gauss law, Ampere's law, and then Faraday's law, okay. And finally you also have the divergence of magnetic field is equal to 0. So these are the four Maxwell's equation in which it is obtained, okay, by solving all the four different laws. Okay, so if you want to remember the Maxwell's equation, go back to each law, like Faraday's law, Ampere's law, and see what is happening there. Okay, so in these classes I cannot teach like all the Ampere's law and all those things because it's already there. Okay, so I suggest you you can go to this Introduction to Electrodynamics by Griffiths. Okay, it contains all this information, okay, and it also has all the details regarding this particular session. Okay, So for today's classes, there are 5 questions. So I have completed all the 5 questions. I will also upload the notes there in the drive. Okay, you can take a look at it. Okay, whatever the solution that we have solved just now, I will also upload there so that you can have a look at it. Okay, so I will stop here for today. Okay, so next class I can see you next week. Okay, next class on next week's. And thank you for joining these classes. See you next week. Okay. Thank you. If you have any questions, you can always ask the questions to my mail or any class or even next week also. Okay. So thank you so much.